Why would a machine that costs as much as a superyacht become the switch that decides the future of the entire tech industry? Stay until the end of this video because you're about to see why one of the smallest things on Earth demands the most insane and most magnificent machine humans have ever built. Let's start with an image. This is a computer chip. Tiny. You can slip it into a pocket, put it in a phone, or a laptop. But if you zoom in, you'll find a real city inside. Those multi-story buildings are stacked circuit layers. Those highways are metal interconnects that, if you stretch them out, would add up to hundreds of kilometers, all packed into a piece of silicon smaller than a fingernail. And at the very bottom is the most important thing of all, the transistor. Billions of transistors, the zeros and ones behind every calculation. Chips get more powerful by a brutally simple rule. The smaller the transistors, the shorter the signal paths, the faster everything runs. And the more transistors you can cram into the same area, the bigger the leap in computing power. For more than half a century, the world rode that wave. Roughly every 2 years, transistor counts doubled. We called it Moore's Law, the rule that dragged the entire tech industry forward like a hurricane. But then, around 2015, the whole industry hit a wall. Not because we ran out of ideas, because physics started laughing in our faces. The problem sits inside the most critical step of chip making, photolithography. The basic workflow sounds simple. Coat a wafer with a light-sensitive material, shine light through a mask or reticle to print patterns, then etch, deposit, rinse. And you've created one layer of circuitry. Repeat that cycle dozens, sometimes hundreds of times, and you end up with a multi-layer chip. The bottom layer is where the transistors live, the most complex region. Above it are the metal wiring layers carrying signals and power across the city. Picture a wafer as a thin plate. Hundreds of chips sit packed across it. Every coat, expose, etch, deposit cycle adds another floor to the architecture. And because everything happens at the nanoscale, a single dust particle, a tiny vibration, a microscopic misalignment can turn an entire layer into scrap. So this game isn't just about being smart, it's about being perfect. That's why fabs have to be ultra clean, thermally stable, and controlled like precision laboratories. But there's a lethal limit. Light has a wavelength. As you try to print smaller and smaller features, the openings on the mask begin to approach the wavelength of the light itself. Then the light diffracts, spreads, interferes, and your image blurs. Want to print smaller? You need a shorter wavelength. And that's where the industry got stuck. For years, chip makers relied on 193 nanometer light. Eventually, even with every trick in the book, multi-patterning, multiple exposures, you still couldn't break through the wall. Moore's Law was on the verge of dying for real. And that's when the main character enters, the most important machine on Earth. It's called an EUV lithography machine, extreme ultraviolet lithography. And the only company that successfully commercialized it is ASML in the Netherlands. To understand how absurd this is, this machine costs hundreds of millions of dollars. Not because they want to sell it for that much, but to generate EUV light with a 13.5 nanometer wavelength, you have to do something close to impossible. You have to build an artificial sun inside a clean room. EUV doesn't behave like normal light. Air absorbs it, glass absorbs it, lenses are useless. So to use EUV, the entire optical path has to run in a vacuum. And instead of lenses, you need mirrors, special mirrors that can actually reflect EUV. And those mirrors have to be polished to a level that sounds like science fiction. If you scaled one up to the size of Earth, the tallest bump on its surface would be about as thick as a playing card. That's atomic level smoothness. But where do you even get EUV light? This is the part that makes engineers swallow hard. ASML uses molten tin, firing it into tiny droplets at insane speed, tens of thousands of droplets per second. Then they hit each droplet with an extremely powerful laser. Not once, multiple times within a few dozen microseconds. The first hit flattens the droplet into a pancake. The next hit fluffs it up, lowering density. And then the final main blast turns it into super hot plasma, emitting EUV light at exactly the wavelength they need. In plain terms, every tin droplet becomes a tiny explosion, repeated around 50,000 times per second. A chain of mini supernovas inside a vacuum chamber. And the terrifying part is, you can't miss. If timing slips, EUV output drops, throughput collapses, and an entire fab's production slows down. Now think about it. Tin is exploding. Debris is flying everywhere. But sitting right nearby are the most expensive, most flawlessly smooth mirrors on the planet. If even a thin film of tin contaminates them, the whole optical system can be crippled. And this machine has to run 24/7 in a production fab. There is no room for error. So they pump hydrogen gas to help clear tin debris, protect the mirrors, and still maintain precise control of heat, pressure, and flow. Get it slightly wrong and either the mirrors foul, or the EUV is absorbed, or the system overheats. But even that isn't the final boss. The last problem, and the reason EUV becomes the world's most important machine, is accuracy. When you print layer upon layer, they have to align almost perfectly. If they don't, transistors and interconnects miss each other and the chip fails. EUV has to align layers so precisely that the overlay error is on the order of a few atoms. You heard that right, a few atoms. Meanwhile, inside the machine, major components still have to move with extreme acceleration to hit production speeds. It's like driving an F1 car while sketching with a pencil on a single strand of hair while landing every line at atomic precision. And the impossible part is, they did it. When EUV entered high-volume manufacturing, it rescued Moore's law. Every leading-edge chip today, phone chip, an AI chip, a server chip, it depends on these machines. So why do I call it the world's most important machine? Because it's not just another tool in a factory. It decides whether we keep shrinking transistors, whether AI keeps getting stronger, whether smartphones keep getting faster. A chip can be so small you could drop it without hearing a sound, yet to create it, humans had to build a gigantic system so complex, so precise, it borders on madness. And here's the most memorable part of the story. For decades, most people said EUV was impossible, but a small group stayed stubborn. They kept chasing 13.5 nanometer light, atomic smooth mirrors, and tin explosions 50,000 times a second. If they'd been just a little more reasonable, we might have been stuck since 2015. So look around right now, your phone, your laptop, the AI running in the cloud, and remember, behind all of it is a massive machine inside a clean room, creating an artificial sun to print circuitry so small it rewrites what precision even means. That's why I call it the world's most important machine. If you found this useful, please give it a like and hit subscribe. It's the simplest way to support high-quality content and help the channel grow. See you in the next technology and economics breakdown.